Hello, my name is Ryan Mitchell. This is the video for the final project of computer graphics course for spring 2022. So in this project, I'll be doing deferred shading or rendering. Additionally, I have a real-time light count adjustment with a shader using a shader storage block or a uniform buffer object, and a custom object loader built in with a lot of easy buffer support. Like frame buffer support, vertex buffer support, index buffer support, vertex array. Just makes it really easy to load objects and use them and modify the transforms and so on. And finally, just a little extra, ImGUI integration with speed log integration for Logi. ImGUI, by the way, for GUI stuff. So yeah, let's just get right into it. So if I run the program here, you can see it is completely unlit at the moment. If I go to my handy GUI here, I can very much increase that. I'm already 156 lights, which is kind of fun. I can move around, of course. And yeah, let's just bring that way up. So this is 1,024 lights, which would and still running at a solid 80 FPS right now, which is kind of funny. It was running at 2,000 FPS, right? Well, it looks like right now 1,200 since I'm recording, I imagine. But yeah, so this basically the concept of deferred rendering is that rather than rendering the lights on all the backpacks, so normally, when you would try to render the geometry of a single backpack, you would have to try to apply all the lights in the scene to it, right? And so then you do that for each backpack. So basically, the number of rendering things you have to do is the number of lights times the number of backpacks. Well, with deferred rendering, what we can do is we can render all of the backpacks first and render that into a frame buffer. And then in a second rendering pass, second shader really, we can render all of the lighting on the actual pixels of that frame buffer. And the nice thing about that too is that it's already been depth tested and so on. And so really we just have a frame buffer, the screen width times screen height pixels, and we can sample from saved textures the position of the pixel we're looking at, and of course the color of the backpack and the specular of the backpack, and then apply lighting as you would normally do to it. Which is really cool, because then in that case we actually only need to do the number of lights plus the number of backpacks or number of models kind of work, which is a lot lower, and that's why we're able to achieve such nice FPS here. Even though we do have a solid number of backpacks, 9 backpacks, which is pretty high, and of course 1,000 lights, and so you can imagine that the magnitude can really quickly increase with lighting if you're not too careful. And something that can make this even better too, which I'm not doing, is right now the lights, I kind of calculate lighting for the backpack, or for that particular light, even if its radius is even if it's gonna completely attenuate by the time it gets to the backpack. So lights do have attenuation, but I'm gonna calculate right now. It calculates the light anyway, just because it's honestly wasn't that big of a deal. But that would be an additional optimization that you could make. So yeah, and here goes. There's the logging too. I'll show that really quick. Doesn't make not too important. You could use any kind of logging library you want and so on. But yeah, if we get to, let's just take a quick look at the shaders. I don't want to take up too much of your time. So first of all, here's the first shader where we're rendering actually the geometry of all the backpacks. As you can see, it's pretty simple. We just have the 2 textures. In this case, for a backpack, we're only using the diffuse and specular. You could also do something similar with a normal map. You could just save the normal map in an additional texture. But in this case, we're just using the normals that are loaded in from the object file, as you can see. And well, we just save out the information that we need into 3 more color attachments, right? Or in this case, rather, so into 3 color attachments. So we need the position color attachment, normal color attachment, and the albedo color attachment. Albedo being just standard color diffuse, right? And well, what's nice about this is that we can save the normal diffuse texture RGB into the albedo RGB, And then we can also use the fourth component to the alpha to save our specular, because specular is just going to be a single 0 to 255 value. And then we just save out, of course, our fragment position here and our normal coming in from our object file. And so then in the when we go to actually do the lighting, and this is after, this is rendered into a frame buffer. And now when we're trying to do lighting on that frame buffer, well, it's not too bad, because as you can see, we just have the 3 textures coming in, same as the textures were coming in from the image files last time: position, normal, albedo. And then we just light it as we normally would, applying, getting light direction, figuring out what the diffuse is going to be based on the diffuse and the color. Diffuse coming from the albedo, and color coming from the light color, rather. And of course we have here's the light position right here, which we're going to use to calculate the light dir. And then we can also calculate what the final color should be based on the attenuation that's determined by a linear and quadratic factor. Finally, we just add that to a lighting vector. And of course, we do also have a very small ambient, which you could see, because even when I had the light all the way off, you could still somewhat see the texture. And then we just apply the fragment color. So that's all pretty standard. The other thing, though, which is what I briefly mentioned at the start, is we're also using a shader storage buffer. And so this is denoted right here. Basically, it just lets us store as many floats as we want to into this buffer right here. And then I can just use that light data to fetch our position, color, linear, and quadratic. And that lets you use as many that lets you use a uniform for the number of lights, instead of what you normally do, which is just a const number of lights, and you would have a struct and so on. And you can see it's complaining because it needs to be initialized, but this lets me not initialize it and just initialize it in the actual program, which is great. And then finally, of course, I do also just render some cubes, and those cubes are rendered using, here we are, here we go, light box. It's just the color of the light. And so that's why you get a whole bunch of lights floating around that look like cubes and are easily applying lights to the backpacks. So the way that looks in the code, I'll do a quick run through it. Here we are. Well, first of all, we're going to initialize our shaders, and then we're going to create our object manager and load in the object shader that we need. And then we're going to create a whole bunch of positions for our backpacks. And well, the object manager just lets you specify the images you're going to use for your textures and the texture type that you want that to go in, and that will correspond to actually the variable that is used in the fragment shader, or vertex shader, I guess, depending on what you want to do with the uniform. And then you can just pass in your object file. And then for each position, you can see we just create the object from the object handle that is returned by the manager here, and we can then translate it and scale it accordingly. We have access to its transform now. And then we're just going to create a frame buffer, bind to the frame buffer, add the color attachments for that. We're going to make sure that OpenGL knows that it's using these 3 attachments. And then we're just going to set its render buffer using the GL depth component and GL depth attachment, which you can see if we go into here. We're declaring the render buffer storage, and here we are, GL frame buffer render buffer. So just do something with depth. And then we're going to unbind it. Finally, now we can actually set up our shader lighting, or rather the lighting shader. And so we're just going to set up those 3 textures to correspond to the correct color attachments. If I swap these around, I would also just swap these around. Okay, so finally, let's also generate the uniform buffer. In this case, we do just as you would with any other buffer. Gem buffer is bind buffer. And then we're going to generate a whole bunch of data on the CPU to eventually push into the uniform buffer, but not quite yet, because we might change the number of lights we need. So yeah, here we are. We're just doing some rendering, some IMGUI stuff. And then let's bind to our frame buffer. Make sure the frame buffer is the correct size. and then we're going to update our objects in the scene, and do a render. And then we can just unbind. And so that draws all the backpacks into the frame buffer. And then we're going to use that frame buffer to actually render lighting onto it. And so let's make sure we clear the GL color buffer bit, GL depth buffer bit before we do that, so it doesn't mess with our lighting. And then we're going to bind the uniform buffer, allocate the correct amount of data, which is just floats times number of lights times 8 in this case, because we're doing position, color, and 2 constants. We can set our uniform, and then we can make sure to generate extra lights if we need to, if number of lights increased. And finally, we're going to actually pass the data into the uniform buffer. And then we can unbind from it because we're no longer using it. And then we can just render the single quad. Render quad just creates a VAO, creates a VBO, and so on. Cool. So now let's copy that data from the read frame buffer, or rather from the original frame buffer into our default screen frame buffer. Then we can bind to that. Excuse me, and then we can just copy that over with GL frame buffer. And then lastly, we're going to iterate over all of the lights in the scene and just render a cube for all of that on the default frame buffer. And so what you can see, if I go into here and bring up the geometry, you can see it is, you can see we can see one frame buffer in the scene because you can see like the quad here, and then it also shows the geometry of everything else, which is great. Yeah. Very neat. And then we're just going to render IMGUI stuff and slot buffers, and that's that. Yeah. So that is all that's going on with this project. Feel free to poke around and look at other stuff. But yeah, thanks for listening. I hope you enjoyed the presentation. I hope you saw that deferred rendering is pretty cool.